In today's video, we're going to look at the Schmitt Trigger, which is this part of the circuit. I'm using a trimpot and a resistor for our input. It's a voltage divider, and so since half the resistance is fixed, we can go anywhere from 2.5 volts down to 0 volts as our output. We'll get to that later. That's our output for the trimpot, the input for our Schmitt Trigger. The output for the Schmitt Trigger, I attached a load here. Load doesn't really matter other than what it does with the output signal, but we got the output there with the jumper there, so I don't have the load on the schematic. But in any case, let's get to what the Schmitt Trigger is. So I'm going to pop this out. We'll do a step-by-step build of this circuit coming up. But first I want to demonstrate some things. So we're going to take the trimpot, and I do this quite often, and the jumper's kind of in the way. There we go. But now I have it attached directly to the transistor base. The collector is up there, emitter down there. There's a space in between the pins, and I did that in an earlier video, and I just kind of left it there. But now you can see the LED is on, and of course if I turn the trimpot down, then the LED turns off. Right now it's in the active region. It's on somewhat, but not all the way, and that's one thing that the Schmitt Trigger fixes. So let's look at that right now. We should turn the power off while making adjustments, but it'll be okay if we don't. I'll be careful not to short circuit anything. And now we'll look at how the Schmitt Trigger improves the turning on and off of this LED. Power supply is on, of course, and so right now the LED is off, so we're going to raise the voltage by turning the trimpot. There we go. You can see it suddenly turned on. Slowly turning it down, and it suddenly turned off. Let's zoom in to get a better look at that. But that's one of the main things, is that it suddenly turns on and then suddenly turns off. But you'll also notice it doesn't switch on and off at exactly the same point. If it's already on, like it is now, we have to turn it down a little bit before it turns off. Now we have to turn the trimpot up a little bit before it turns on. So that's known as a hysteresis. It's not an exact point, so if you have a moving voltage that just kind of sits in one area, moving up a little bit or down a little bit, it doesn't just keep flickering on and off. It tends to stay in the on or off position that it already is in. You have to add some extra movement to make it change states. So now let's get to the actual step-by-step build of the circuit. And the our control here, our trimpot and the fixed resistor, that's just a basic voltage divider. I'm not really going to go over that. The transistors, that's where we're going to begin. They are NPN type transistors. You can see the arrows are not pointing in, NPN, and it's very important to pay attention to the arrows on the schematic. If they were pointing in, of course they'd be PNP transistors. So I'm going to use the 2N2222, the most commonly known NPN transistor. The flat side is facing us, so left pin's the emitter, middle pin's the base, right pin is the collector. And since this is I think the 9th transistor video I'm making, I assume you pretty much know this stuff, but just in case you don't, I'll run through it quickly now. So if I turn it this way, now the collector is on top, base is in the middle, and the emitter is on the right. And I already have jumpers to show where the pins go, but as you can see, we got the collector going to the base of the other transistor, and then the two emitters connected together. So I have a gap there to leave the base floating for right now, but that jumper goes to the collector, and then it will go down to the base of the other transistor, which I have right here. and then the two emitters we have connected together. So I actually got this particular circuit. It's not the exact same. The resistor values are different, but I got this particular circuit from a book called The Art of Electronics, and it's the simplest one to put together that I found as far as Schmitt Trigger circuits going. There's other circuits that are a bit different out there that you could build if you prefer them, but I think this one's the easiest, so I'm going with this one. So now we got these two resistors, and they go to the positive side of the power supply to the collector of each transistor. So I think I'll do this one first, try to angle it there. There you can see we have the collector up there. Make sure we get to the positive rail there, and I'm using 470 ohm resistors. The value of these resistors is the main thing I changed, and I used these three values, or actually these are the same value, but also this value resistor down here, to give me a little more, I don't know exactly the right terminology, but that range of hysteresis. I picked these resistors, so I had to move the trim pot as far as I could before it would change states. And with different value resistors, I didn't have to move it as far before it changed states, but that doesn't show up as good while making a video. So you can adjust the resistors. The main thing is to limit current to a safe level. Again, we're going to the positive rail to the collector of this one. The most important thing is to limit current to safe levels, and then everything else you can adjust the value of the resistors till you get other properties of the circuit you like. So there we go. And these are not very stiff legs for these particular resistors. I read other reviews for other resistors have stiffer legs, so if that's important, look for that. But I like the range of values of these resistors. So this one's only 22 ohms, very low value resistor. We could also connect these directly to ground. So if you don't have below or down to a 22 ohms, I think it was 56 ohms, it still worked. But 100 ohms, the circuit did not work. So if you don't have these lower value resistors, you can just take a jumper and go directly to ground. Doesn't matter, but this 22 ohm resistor helped give me some extra range for that hysteresis so that you could actually see the movement on a camera. So really, that's it. Make sure we go to the negative rail. I actually just shot this scene earlier, accidentally put it to the positive rail. The circuit wasn't working right. The output actually just stayed on, and so I reshot the scene. But that's all it was I had it to the negative rail instead, to the positive rail instead of the negative rail. So double check your wiring and make sure it matches up. So this is the ground symbol, which is the negative side of a DC power supply. The VCC, or the 5 volts, whatever, however they indicate it, that's the positive side. So now let's take jumpers, and I'm not color coding these. I just grabbed a blue jumper and a red jumper because that's what I have floating around in my commonly used pile of components. And we're going to go to the base of this transistor. That's the input for our Schmitt Trigger, output for the trim pot there. And then our output for the Schmitt Trigger is the collector of this other transistor, as you can see there. And I have a jumper a couple spaces away so that I can just put an LED directly to there. We don't have to have the transistor with LED, but for the load for right now, we're going to use it. So you can see that transistor there. As I said before, the pins are separated. That's just something I did for a different video. But we're going to plug the output of the Schmitt Trigger to the base, the middle pin of that transistor. So now let's turn the power on and see how we're doing. The LED is on, but you can see the arrows over there, so the voltage is relatively high. And try not to block anything shadow wise, but there you can see Now the LED is on. Now it's off. And we got a range of hysteresis here before it changes states. So we got that range because of the value resistors that I picked. Mostly that's the main change I got for different value resistors. Exact values don't matter. Use what's most conveniently for you, but 470 is commonly available. Most schematics you'll probably see it say 1 kilo ohm. It works pretty much the same. Let's right now turn the power off. I'm going to yank the output here and then take the LED here, and the legs have already kind of been spread before. Again, this is an LED, a diode. The anode is the longer lead because we haven't trimmed it. The cathode, the shorter lead. For the LED to turn on, cathode also has a flat little edge here that doesn't show up on camera. But for the LED to turn on, the anode needs to be more positive than the cathode by about 1.5 volts. Slightly more than that. So what we're going to do is, this angle is easier to see. Long lead the anode, we're going to put to the collector of the transistor. Short lead the cathode. We're going to go to where that jumper goes to ground. Now I'll turn the power supply on. And the LED is not going to be as bright. That's the main difference here. But let's turn it down. You can see it suddenly turns off, suddenly turns on. Pretty much exactly the same. So the load doesn't really matter other than what the load is doing. It's taking a signal from the output, whether it's an LED directly going to ground, or taking that signal to the base of a transistor so you can amplify that signal as far as the load is concerned. So now let's make a couple of modifications. As I said before, we don't need a resistor at the emitters. I just found that the 22 ohm resistor gave me a little bit more movement before we change states. And so now we just have the emitter connected directly to ground, and I will demonstrate that. I'll turn this down now. So voltage point is going to change, but there you can see that we still have some hysteresis. I got to move this a little bit, but hardly any. It's not showing up on camera near as well that I have to move at all. So that was the main reason why I used the 22 ohm resistor. As I said before, you could just connect it directly to ground, which we have there. So now we have an even better solution. I'm going to take a 470 ohm resistor. This value just worked the best for what I want to do in this video. You don't have to use exactly this value. Same with the ones up there, but it's the same value as these two. I'm going to connect the output directly to the input. This will give us what's called positive feedback. So we're going to feed some of the output signal to the input. And let's see how that improves the circuit as far as I'm concerned. So now, so it's on. Let's go down, turn it off. As you can see, we turn it off down there. And now we got to go all the way up to there before we turn it back on. So as you can see, I don't know the exact terminology, but the range of hysteresis is the best I can explain it with right now, is a whole lot wider than it was with just the jumper there without positive feedback, or even the 22 ohm resistor. And so there's slight modifications you can make like this to this circuit, but positive feedback is probably the best one for increasing that range of hysteresis there. So now moving along, I added the current pads, and it's not all current pads, also voltages indicated here. I'll talk about that coming up, but while it's on, first let's take a look at the output. So as you can see, the output, it comes to the collector of this transistor, and then the other side goes to the 5 volt, in this particular case, power supply. And so as you can see here, when the transistor is off, I like to do this. Basically, it's as if it doesn't exist. So now you can see the output should head towards the negative side of the power supply at some point, which gives us a current path there. And so the output tends to want to be on, have a positive voltage and current going that way. That's why when we put the LED directly to ground, it turned on. So now, also, we have this resistor here that wants to go to the base of the transistor. So we'll look at that actually coming up next. But when this transistor is on, because again, we have a positive signal going to the base of the transistor, which can go to ground, that turns that transistor on. Transistors are electrical switches when they're not being used as amplifiers. And so it's making this conduct fully, so it's almost like a piece of wire. And so we have a path there, and this side of the resistor is basically connected directly, other than through this resistor here, to ground. So that's going to pull the voltage down to about 0 volts here. And so there's going to be a voltage across here. That's the main thing that's going to set the current. There's also a voltage across this resistor that sets the current a little bit lower. But in any case, we're going to have about 0 volts here. This transistor is going to be off. So it's pretty much as if the transistor doesn't exist. And so we just have a current path there, pretty much unimpeded. So now let's go over here to where the output is off. And so that's when we turn the trimpot down towards the negative rail. We get a low voltage. That turns this transistor off. In the diagram over there, it was on, but now it's off. So pretty much as if this part of the circuit does not exist. And so now we have a direct connection from the positive rail through the resistor. The resistor is going to limit current, of course, but for the most part, the signal gets to the base of the transistor. It's going to be above about 0.6, 0.7 volts, and so it's going to conduct through there. That's going to allow, since we got enough current going through the base to emitter, this is also going to lower the current, as I said before, this resistor here. But in any case, there's enough current going from base to emitter to get this transistor to fully conduct. So now you can see that the voltage at this point is going to be pretty much, not exactly, but almost 0 volts to the negative rail. And so of course for the LED especially, you need about 6 volts for it to begin conducting. It's going to block about 2.2 volts once it's fully conducting, about 20 milliamps. But to get some current to flow through it, you're going to need about 1.6 volts. So it's dropped down to about 0 volts, and so there's not enough voltage to especially power an LED at that point. And that's how we get the off state. So when the input is off, this transistor is off, allowing that transistor to conduct, which makes it so our output is off. It's about 0 volts. And then moving along to this part of the diagram, I have I think what's called a hysteresis loop, but you'll see this a lot. And other components have different looking loops, but this gives you the basics of what's going on. So while the output is off, and right now it's mostly off because the power supply is off, but the output is off, we have a line here, so there's a lower voltage here and a higher voltage over there. As we said before, the exact voltages will change based on how the circuit is built. And so, in fact, let's add the 470 ohm resistor. Oops. There we go. Give some positive feedback. And right now, we're in the off state, and we have a range that we can turn it up and it stays off. So once we get to that point though where it turns on, which is right there, now it jumped up to this point of the circuit, and we can either go higher or go lower for a bit and it will stay on. So let's just go lower, and we can go higher. But if we lower it right to a certain point, then it's going to go off. And again, the exact value depends on the exact components we're using and whatnot, but either way, there's a point where it will turn on and then stay on across a wider range. You go down a little bit, it stays on until you hit that point where it turns off, and then again it stays in that range until you hit a point where it turns back on.